So we'll start from where we left off. So in the last class, we started with this motivation that recurrent neural networks have this problem of vanishing and exploding gradients, and we wanted to arrive at some principled way of avoiding this. So you were first started with this intuition that in many real life situations, like for example the human brain or the whiteboard, we tend to do these three operations called selective read, selective write, and selective forget. And they essentially help us in dealing with these finite sized memories, right? Whether it's a whiteboard which is finite sized or your brain or whatever it is, right? So is it possible to kind of improve RNNs which also suffer from this problem that they have this finite sized memory, and hence if you're trying to capture everything from time step 1, then by the time you reach time step t, where say t is 30 or 40 or so on, it's quite natural that whatever you have learned earlier will get morphed to an extent that it just is not recognizable anymore, right? So we wanted to deal with this problem, and with that we motivated selective read, write, and forget, and then we introduced some equations or converted this into a model, and this is the diagram that you see is the model. Actually that's the LSTM cell, yeah, and it has these three gates, output gate, input gate, and forget gate, and which perform these three functions of selective read, write, and forget. So intuitively all this was fine, but we need to be more technical in terms of we are trying to deal with the problem of vanishing and exploding gradients. So how does it solve that problem? All that makes the story seems fine, but how does it actually relate to the math? So we saw some intuition for that, and the intuition hinged on this observation that during forward pass, the gates control how much of information passes from one state to another. And in particular, if you have the situation that from one time step to another, say the forget gate tells you that keep forgetting 0.5 of the previous state, then by the time you reach say the 100th state, you would have forgotten 0.5 raised to 100 of the first state, right? So that means even during forward pass, the information from state 1 vanishes. So if it vanishes during backward pass, that's also fine, because state 1 did not contribute to state 100, right? That was the intuition that all this hinged on. Now we are not going to do much different from this intuition. We're just going to see the corresponding equations for these intuitions and just make a more I wouldn't call it rigorous, but a more mathematical proof on why LSTMs solve the problem of vanishing gradients. And we'll also show that they actually don't solve the problem of exploding gradients, and then we'll see a simple trick of dealing with exploding gradients. Well, that's what we'll do in the remainder of this particular lecture, and then we'll move on to the next lecture in this lecture, okay? So we'll now see an illustrative proof of how the gates control the flow of gradients, right? So recall that this is the control, this is the flow diagram or the dependency diagram that you had for RNNs, and in particular because you were dealing with an ordered network, you had these explicit and implicit derivatives, and finally you came up with this multiplicative form, and this term here is actually a matrix because it's a derivative of a vector with respect to a vector, and then this same matrix was getting multiplied multiple times, and then we did this proof which showed that this term is actually lambda gamma, okay. It's actually proportional to this term, right? And as if lambda into gamma is greater than 1, then this will explode. If it's less than 1, then it will vanish given sufficient time steps, okay. Now in particular what was happening here is the following, that you have this loss at time step t, here the time step is 4. Now what if this loss or this error occurred because W was not good enough to compute a good value for S1, right? So W was at a certain configuration, based on that you computed S1, and that S1 was not good enough, which eventually led to the error at time step 4. All of you can imagine the situation that, I mean, you're not being able to do something well at S1. Now this needs to be told to W so that it can improve, right? And that information has to come through S1. That information is already going from here, but this information is about how badly it performed in computing S4. This is not how badly it performed in computing S1. So that information has to travel to W all the way through S1. And that was not happening because this path, don't look at the bullets, this path was actually vanishing. Right? That's what this multiplicative term says, right? As the number of time step increases, that path would vanish. Okay, so that's the actual problem that we are trying to deal. So now, what's the general situation here? Right? The general principle is that the gradient of L theta or at a particular time step, say here we are considering L4, so I'll just call it LT. With respect to any parameter theta I, the parameters are W, U, V, B and C. With respect to any parameter, it would vanish if all the paths leading to that parameter, if it vanishes. So with respect to this particular path, so that's the only path which leads to W through S1. If there were multiple paths, if there was say one such direct path, right, if we had used some other kind of a connection which gave us this direct path, then it would still have been fine. But there was only one path leading to W through S1, and if the gradient vanishes along that path, then the gradient will vanish. Okay, if there are multiple paths, then only if the gradient vanishes across all the paths, then the gradient would vanish. Is that fine? What's the corresponding rule for exploding gradients? If there are multiple paths, the gradient would explode if it vanishes through any one, if it explodes through any one of the paths. Okay, so these are the two things that we need to consider. Okay, so to prove that in the case of LSTMs this does not happen, for the first case we'll have to show that there is at least one path through which it does not vanish, and for the second case, because we are going to show that it explodes, we just have to show that there is at least one path through which it can explode. Okay, so these are the two things that we need to prove, and the first thing that we are going to focus on is the vanishing gradient problem. Okay, so we'll start with the dependency graph for LSTMs. That means I want to draw something similar for LSTMs involving all the different elements in LSTM. So what are these different elements? The two rhyming things, one being gates, states. Okay, so gates and states. Okay, that these are the two things that we care about. So let's look at all these. So starting with the states at time step k minus 1. So at time step k minus 1, you have this two states sk minus 1 and hk minus 1. Okay, using hk minus 1, you are going to compute the output gate at time step k, and this also depends on these parameters w, o, uo and bo, right, which is obvious from the equation. Just to make sure that this diagram remains tractable, I am going to get rid of the parameters and I will come back to them later. So right now we will just focus on the states and the gates. Okay, and then you have these other intermediate states and the other gates, right? So you had fk, you had ik, so you had these three gates, the temporary state, and then what else? What are the other two things at time step k? So we saw this diagram about all the computations which happen at time step k, right? How many computations happen? 3 states and 3 gates, right? So you've seen the 3 gates and this one temporary state. So which are the other two things? There's no selective forget with you guys. There's only everything forget. Hint, look at the gray cells and change the time step. What will you get? I mean, are you all, I mean, we did LSTMs 2 days back, right? I mean, are you all okay with that, or do I need to revise something? I mean, I don't need to revise it, but do I need to, is it fine? Okay. So sk and the other thing is hk. Okay, and remember that sk also depends on hk. Just stare at this for 30 seconds and make sure that you are okay with it, right? All the equations are there. These are the 6 equations that, or the 6 computations which happen at time step k. There are 3 gates and 3 states, and the dependency graph is obvious from these equations, except for the fact that I've ignored the parameters. How many of you are comfortable with the equations and the graph, corresponding graph? Please raise your hands high. So I think it should be okay, right? We have these 6 equations and we have this dependency graph. Now, so what happened in the graph is we started from sk minus 1, hk minus 1, and we reached sk and hk, which were the outputs at the next state. Now what will happen from here? We are looking at recurrent neural networks. Recursion is the answer. What will happen now? The same graph will keep recursing, right, for the next time step and up to the last time step, right? Does that make sense? Okay. This looks much more complicated than the dependency graph that we had for RNNs, right? But just because there are so many, in RNNs we just had this one state and no gates. So here, but we have these 3 states and 3 gates. That's why there's so many paths. Okay. Now for simplicity, what I'll do is I'll not draw separate nodes for the parameters. Although in the case of the RNN dependency graph, I had drawn them separately. What I'm going to do is I'm just going to put the parameters on the corresponding edges, right? So fk actually depends on wf. It also depends on uf, and it also depends on that bias, but I'm just going to take a small set of parameters. I'm only going to focus on the w's, not the u's and the biases. Okay, this is only for illustration, for no other reason, right? And whatever arguments or proof that we are going to see, it holds for all the parameters, but we just need to prove it with respect to one parameter, and the same story repeats for everything. Okay. Okay, so this is the dependency graph and these are the parameters. Now, what I'm interested in knowing is that there was some loss at time step t, and maybe that loss happened because WF was not good enough to compute SK. Of course, WF computes FK and then FK helps in computing SK. But maybe WF was not, I'm just short-circuiting it and saying that WF was not good enough to compute SK, right? And that's why I want the gradient to reach to WF through this SK. That's what I want to do, okay? And this is exactly what I said. I'm interested in knowing that if this loss can reach WF through SK, right? So all the three highlighted things are what I'm interested in. I'm interested in the path to WF through SK. Of course, there are many other paths to WF, but they don't account for the problem in SK. Is that fine? Everyone is clear with the setup? Okay. Now, and we can ask similar questions about all the other parameters, the W's, the U's, the input gate parameters, the output gate parameters, and so on. Right? There's nothing so special about WF. The same question holds for all these other parameters also. Okay. Now, how does LSTM ensure that this does not vanish? So let us see that. As I argued earlier, it is sufficient to show that this gradient does not vanish. Okay, if I can show that this gradient does not vanish, then I'm pretty sure there's no recursive connection here because it's just a single connection. So there's no recursive connection here. So if I can show that the gradient reaches up to this point, then after that I can be sure that it is going to reach WF. Everyone buys that setup, right? This is what I need to show. So to prove that the gradient reaches WF, I just need to show that it reaches SK. That's the only thing that I need to show. And so first thing that I'm going to observe is that there are multiple paths to reach to SK. Which are these paths? One through SK plus 1, because SK contributes to SK plus 1. The other through HK, which is visible. But now also notice that how many paths are there to reach to HK itself? 4, not 4 actually, that's going to be combinatorial, right? Because there are 4 outgoing edges from here, but then again there will be 4 next stage and 4 next stage and so on, right? So let's not count the number of paths, but let's just convince ourselves that there are many paths to reach to SK from LT theta. Everyone is convinced about that. We are not counting the exact number of paths, that's not very hard to do. But all we are saying is that we know that there is one path through SK plus 1, one path through HK, and HK itself seems to have many incoming paths during backpropagation. So there are many paths which are reaching from LT theta to SK. Everyone is convinced about that. Anyone who has a problem with that? Now to show that the gradient does not vanish, what do I need to show? Of all these paths, just say it, there exists at least one path through which the gradient can flow. That's what I need to show. Okay. Even if it vanishes across all the other paths, I'm still fine with it. Okay. So now consider one such path, which is this highlighted path. Okay, that's a valid path to reach to SK. Now let us denote the gradient along this path to be T0. And the total gradient is going to be a sum of many such paths, right? So I'm calling this path as T0, and this is what the gradient looks like. Okay. So this is simple, just this red path, the next red path, and then this series of problematic multiplications, right? You have this recursive multiplications again. So everyone agrees that red is good. The red path, there is no recursion, the gradient will flow, right? We just need to focus on the blue path. Everyone is convinced about that, right? Okay, so that's good. The first term is fine, as I said, because it's directly connected to LT. There is no recursive or no other intermediate nodes, so the gradient will just flow through that. There is not a problem there. And now we look at the other terms, which is first is dHT by ST and the other is this. Okay. So let's look at dou of HT by ST. What is this going to be? Tensor, vector, matrix, scalar. At this point in the course, I want a unanimous answer. Matrix, right? And recall that in particular, the equation was of this form. Okay. So what's the derivative going to look like? Even without computing, can you tell me something profound about it? It will be a dash matrix, big matrix. How many of you say diagonal matrix? How many of you don't think it's a diagonal matrix? Please raise your hands. Total sum is never 1. So remember that HT is equal to HT1, HT2 up to HTD. Then you have OT equal to OT1, OT2, OTD, and ST equal to ST1, ST2, STD. So HT2 depends only on OT2 and ST2, right? It does not depend on, in particular, it does not depend on any of the other STs. So we have already seen this before. In such cases, what's the ijth entry of this matrix, of the gradient matrix? Derivative of ht I with respect to stj. Which of these terms are going to be 0? Wherever I is not equal to j. That means it results in a diagonal matrix. Okay, so that's exactly what is written here, and the diagonal elements are going to be this. Is that fine? Everyone okay with this? Okay. So now this diagonal matrix which contains this on the diagonal, I'm going to represent it by the following notation. Is that okay? Fine. So this is a diagonal matrix where every element is, this is actually a vector, right? Everyone agrees this is a vector. So this vector is along the diagonal of this matrix. How many of you get this notation? If you don't get this, you'll not understand anything else. Okay. Now let us consider dou st by dou st minus 1. Okay. This is what st is equal to. So what's the derivative of dou st by dou st minus 1? ft, right? ft, right? What else? Why no? Why are you rebelling? What? I mean st only, right? If it is. Can you treat this as a constant? No. Why? Because this is a dash network. Okay. So in an ordered network, the derivative will have two terms. Which are those? Explicit and implicit. In the explicit term, what do you assume? The other terms to be a constant, right? Okay, fine. So the s tilde t also depends on st minus 1, so we cannot treat it as a constant. So once again, this derivative is going to contain an explicit term and an implicit term. Now I'm going to make a worst case assumption. Okay, I'm making this assumption that actually the implicit term vanishes. Notice that this is not favorable to me. I'm trying to prove that the gradient does not vanish. The gradient is a sum of two terms. I am saying it, let the worst case be that one of these terms vanishes. Okay, so this is not a favorable assumption, this is a unfavorable assumption which I am making. So that's fine. Okay, so I am making the assumption that the implicit term vanishes. So what's the explicit term actually? ft. And what kind of a matrix is that? If you agree that it's a matrix, first of all, it's a diagonal matrix again. And what's the diagonal? ft, right? So I'm going to represent it as d of ft. Is that fine? So remember that the original equation had three terms. All of these, the last blue ones were all identical. So this is not problematic because this is directly the last layer. This we have already derived a form, this is some diagonal. And now for each of these we have a form. Do you get that? These are the three parts that we have done so far. So let me just substitute them. This is what it looks like. Okay. Now this is a product of diagonal matrices. What will the product look like? A diagonal matrix. And each element on the diagonal would be a product of all those things, right? So is it fair if I write it as this? Right? Which I can write it as this. Okay, now just stare at this equation and tie it back to the intuition that we developed. Something about the gates regulating the flow of information. You have a multiplicative term here, right? Whenever there is a multiplicative term, we have a problem because remember these gates are between 0 to 1. So there is a chance of vanishing. Everyone sees that? You are multiplying t terms, all of which are between 0 to 1, so there is a chance of vanishing. But I am going to end this proof by saying that the gradient does not vanish. So what am I going to do now? Okay, I'll make this statement. The gradient could vanish, but this kind of vanishing is fair. What do I mean by that? Now when will the gradient vanish? If this product of the forget gates vanishes. But if the product of the forget gate vanishes, that means what would have happened during the forward pass? That information was not carried all the way back, all the way front to time step t, right? Do you see that? Okay, so that's the main reason here, right? So the red term does not vanish, the red terms don't vanish, the blue term can vanish, but it will vanish only if during the forward pass also this multiplicative term had caused the information to vanish by the time you had reached the time step t. How many of you get this? And this is exactly what I meant earlier by saying that if during the forward pass st did not contribute much to st plus 1 because the forget gate was tending to 0, then during backward pass there is no need to pass this information back to st, right? Because during forward pass you did not contribute, so during backward pass why should I hold you responsible, right? And this is absolutely fine to do this, and this is exactly what the equation tells us, that the gradient will vanish only if things vanished in the forward pass. Okay, and the gates are doing the same regulation in the forward pass as they will do in the backward pass. So everything is fair. Is that okay? Right? And thus there exists one path along which the gradients will not vanish when they do not need to vanish. So if during forward pass all the gates were on, that means the information from state 1 was actually carried all the way up to state t, then during backward pass what will happen? The information will go all the way back, right? Is that fine? Okay. So the gradients flow back only when required as regulated by the forget gates, and this is fair, because if you are regulating the same thing in the forward as well as the backward direction, then you are not doing anything wrong. Okay. Now that is a proof for LSTM solve the vanishing gradient problems, or in other words, the gradients vanish only when required and not unnecessarily or arbitrarily as is to happen in the case of RNNs. Now we will show that there exists one path along which the gradients can explode, right? So let us show that path. So consider this path, okay? Now this path is again also active. So if you consider only the path to HK, then it's going to be active for all the gates and all the states, right? So in whatever gates or states you're considering, this path would be there, okay? And this is what this path looks like. You have the derivative with respect to the last layer, and then you have these guys, okay, these pairs, HT by OT, OT by HT minus 1, and so on. Everyone fine with this so far? What is the derivative of HT with respect to OT? We don't remember the equations, so I'll just tell you directly. So based on whatever we have done so far, just trust me that this is what each of the terms in the bracket looks like. You can go back and check this. It just comes directly from the equations. Now what is happening here? Does this look very similar to the situation that we had with RNNs? You had a diagonal matrix and a weight matrix and a repeated multiplication of these, right? And again the diagonal matrix is bounded, the weight matrix is bounded. So now the repeated multiplication could explode. Is that fine? So it does not solve the problem of exploding gradients, but it solves the problem of vanishing gradients. But now still this is bad for us, right? Whether the gradients explode or vanish, our training is going to get messed up. So how do we deal with this? For exploding gradients, what will we do? We'll do clipping, right? So in practice, the way of dealing with this is gradient clipping. If the norm of the gradient exceeds a certain value, then we are going to just clip it to a certain threshold. And this is fine because we care about the gradients only for the direction and not for the magnitude. Anyways, when we introduce a learning rate, we are doing some kind of scale down for the gradient magnitude. So this is just being more explicit and being careful that if the gradients are non-manageable in terms of their magnitude, then we're just going to clip them to some manageable value while being faithful to the direction. And the direction is what matters. So that's why exploding gradients is easy. But in the case of vanishing gradients, you don't have a direction also because the entire gradient becomes zero. So there's no direction there, right? So that's why vanishing gradients is more serious than exploding gradients. And as long as LSTM solve that, we are fine with it. Is that okay? Fine? Okay. So that's the end of this lecture.